So this is going to be your video for rotational force, which is also known as torque. And our goal for this video and this mini lecture is to look at how we can combine Newton's second law, so that F net is equal to m times a, to its rotational component, which is really what we've done with all of our topics leading up until this point. So how we're actually going to start these notes is looking at the mini lab that we did. So looking at what we saw when we had that pivot point, and on that pivot point, we had the meter stick, and your goal when placing the masses on the meter stick was to find the center of mass, or to get it into equilibrium. So we had three masses of varying weights, and you found that you needed to place them at varying distances or varying radii in order to get it into equilibrium, showing that not only the mass but the radius had an effect on that rotational motion. We then continued to discuss the forces that were at play here, which was really only one force, and that was the force of gravity, which is pulling in that perpendicular component, and it did cause rotational motion when this was not in equilibrium. So the fact that that force of gravity was pulling in the perpendicular is actually going to mean something here, and it's going to be a little bit different than our work component, which we know that gravity does not do work, but our work component was that F delta x cosine theta, where it was doing work in the parallel. But in this case, our forces are actually going to be acting in the perpendicular to cause that rotational motion, because if you're parallel to the surface and I push in here, really nothing's going to happen, right? I may push my, station over, my little setup here, but that's really it, and that's a whole different type of motion. But in terms of the rotation in the perpendicular component, that's what's going to matter here. So let's go ahead and start these notes now the same way that we started kinematics, and let's look at forces in the linear and then what it's going to look at in the angular. So in the linear component, we had that forces were shown with a capital letter F. In the angular component, which we know is going to get a Greek letter, it's going to be the letter tau. So this Greek letter is going to represent torque, which has the definition of the force applied in order to rotate an object, or to turn an object. So this force is very specific to that rotational motion, which is why it's going to get the capital or the letter tau. So looking at Newton's second law, we have that F net is equal to m system times A. Now, unlike kinematics, where it had this really clean, if you see this letter in linear, this is what it means in angular, this is going to be a little bit different. It's actually going to look a little bit more like our bridge equation than anything. So in the angular component, our force is actually going to be that tau is equal to RF sine theta. Which actually does, it kind of looks like the work equation, but with the opposite trig function. And instead of traveling a distance, we are looking at the radius, so a distance, in which the force is being applied over in order to rotate that object. And again, it is going to be perpendicular to the surface, because that's the only way you're going to get a rotation. So that's why that sine theta is there. So the R, which really we just call the radius of whatever object you are using in order to turn, it does have a different name. It is called that R is equal to the moment R, or sometimes you hear it as the lever arm, or sometimes you really just call it, the radius. So this is going to be that perpendicular distance between the rotation and a line extended through the vector, because again, forces are vectors, the vector force. So while that is a good textbook definition, I really think just knowing, hey, whatever our lever arm is or what our radius is, that's going to be our R. Now, one thing to note is that we're dealing with forces, we're dealing with vectors, so something has to be positive and something has to be negative. So our direction, in this case, is going to be different than what we're used to. So clockwise is actually going to be negative. Ooh, I'm out of it. Counterclockwise is going to be positive. So what you typically think like, oh, the clock turns clockwise, it's going to be positive. That's not the case here. And I think probably the best way to think about this, that our counterclockwise is going to be positive, is because we're dealing in radians, right? Radians go along with that unit circle. The unit circle goes this way. It goes counterclockwise. So that's kind of my best explanation as to why that's going to be the case. All right, so I'm going to go ahead and pause the video real quick because there's a little bit more that we need to do with this. We're going to find that there's actually two ways to write the equation for torque. So I'll be right back. All right, so we're back, and it's now time. I'm missing a word. Now, time for the Greek. Because the last equation that we had, while it had partial Greek in it, we know that we have a whole component for kinematics that is our rotational component. So it makes sense that we should have a force equation that applies that rotational component as well as just R times F sine theta. So if tau is equal to RF, now, notice that I didn't write the sine theta. That's something, just like work, how we just had it kind of like F delta X and you knew that the cosine theta was applied. If you feel better always writing the sine theta, have at it. But you don't necessarily have to, because it's kind of known that this force is the perpendicular force. Therefore, you're going to be applying the sine theta anyways. So if you want to write it from the beginning, great. If you don't, great. Either way, as long as it's applied, you're good. And I will tell you, a lot of times the theta that we're going to be working with is going to be a 90-degree angle, so it's going to be sine theta of 90, which is just 1 anyways. So that's why a lot of times you see it dropped unless you have an angle that's not 90 and then you see it get applied in. But either way, as long as it gets applied somewhere, you're good. So if we have that tau is equal to that RF, and F is equal to M times A, again, knowing that this is F net and this is mass of the system, then applying this in for F, you get tau is equal to R M A. So that's another way you could write it, but this is just a derivative of these two, right? So this is not something that you could put on your equation sheet, but tau is equal to RF, you could. So we have this, but we want to get to a rotation equation, right? One that has the Greek letters for kinematics. We have our bridge equation that's going to be really good for that. So, and A is equal to alpha R, right? So what we can do is then plug in alpha R for our A and get tau is equal to Rm alpha r, which is a really terrible way to write that. A better way is going to be mr squared times alpha. So let's kind of write that all together here. So tau is equal to mr squared times alpha, which, looking at this, should not really come as a big surprise, because that rotational acceleration, and I'm going to go back to that little mini lab that we did, that rotational acceleration that we had prior to equilibrium was based on the masses that you had and the radii that they were placed. So these two are really big components of that overall torque. But wait, there's a little bit more, because everything up until this point, distance, velocity, acceleration, forces, everything had a rotational component. Mass does as well. And this kind of goes back to that initial inquiry lab that we had, where you looked at those different rotating objects, and you found that when you had the masses where it was spread out over like the large circular disc, where it was hollow in the center, whether it was solid, that distribution of the mass then based on the radius actually did matter in terms of how fast it got down the ramp. So because those pieces matter, they get their own component. So, but mass has a rotational component. Yeah. Because everything gets a rotational component. So just like before, in the linear component, we had that mass was the lowercase letter m. In the angular component, it's actually going to have the capital letter I. And this I is known as the moment of inertia. So think back to Unit 5, where inertia is an object's resistance to change, and it's based on the mass of the object. Here, it's going to be the same thing, except now it's an object's resistance to rotation. So what we actually get is that this mr squared component is our I. So I is equal to mr squared. But what you're actually going to get when you see me in class is a paper, there we go, that looks like this. Because that mr squared is going to be multiplied by different coefficients, so maybe 1/2, 2/3, depending on the type of the object, depending how the mass is spread out, depending if it's hollow, if it's solid. So all of that is going to matter. This paper is not something you need to memorize. You will either have this or you will be given your I. But you're going to see that this component is always there, but it may have a coefficient that it's being multiplied by. And we'll kind of see that in some of our example problems. So knowing that this is I, another way that we can write this then is that tau is equal to I alpha. Because having this capital letter I will then include all of these and all of those coefficients multiplied by the mr squared, which is always going to be the base of that equation. So this last one is kind of a big equation for us because it has the rotational components, and then the tau is equal to RF that has more of the linear component. So we have two different ways that we can apply that tau. All right, now on for the examples.